title of this actual lesson is called Solving Special Systems, but included in that will be the type that we've already been actually solving also. So we're just going to talk about what types of systems are there. We have to be able to name them. We have to be able to talk about what kind of a solution will they have. And there are 3 different types of solutions we can get. As I said, so far mostly every time we've solved a system of equations, we've gotten one solution. We've got an ordered pair solution. There was on that one worksheet you did, remember when we were solving by graphing, you got parallel lines. And what did we say was the solution when there were parallel lines? Was there an ordered pair solution then? To get an ordered pair solution for a system of equations, what has to be true on the graph? Lesson 5.1. What has to be true on the graph for there to be a solution that one solution on a graph? What happens? They intersect. The 2 lines intersect at a point. It's a point they share in common. So when we solve by graphing, we find that point of intersection. But what if the lines don't intersect? What if they end up parallel, as happened in that one problem that we had on that worksheet? What's true then? Can there be a solution? If they don't intersect, do they share any points? Do they have any points in common? No, they don't. So then there's that possibility. Then there's one more possibility, and that third possibility is that they share every point. So in other words, they are the same line. And then we would say that the solution is infinitely many solutions. Not just any ordered pair on the coordinate plane, but all the points on that line that they share. So let's just start talking about how are we going to name these. So a system with at least one solution, at least one solution. So there might be just the one solution, or there might be that what I just talked about, infinitely many solutions. If we have a system that has at least one solution, we call it a consistent system. A consistent system. If it is a consistent system, it can be either, I want you to put a box around that. It can be either, there are 2 choices of what else it can be. It can be an independent one. So independent, if it's a consistent system that we consider to be independent, that means it has exactly one solution. So we know then that means the graph has intersecting lines. Those lines have to intersect. Those lines have to intersect. They have to share that point in common if there's exactly one solution. Well, if lines are intersecting, what has to be true about their slopes? Do they have to be the same? Do they have to be different? Do they have to be opposites? Do they have to be reciprocals? What do they have to be? For lines to intersect, what would have to be true about their slopes? Really? You don't have any idea? Okay, same slopes. What would be true? Would they have the same slope? Would they intersect? No. We learned that same slope with different y-intercepts means what? Same slopes with different y-intercepts means what? Lindsay? Parallel lines. Okay, well, if they're good, they have to intersect, so they can't have the same slope. You can rule that one out. So how about, oh, remember when they were opposite reciprocal slopes, what kind of lines were they? Opposite, the slopes were opposites, so one was positive, the other was negative, and they were reciprocals of each other. What kind of lines did we have then? Perpendicular lines. Well, do all intersecting lines have to be perpendicular? Do they have to be? Do they have to form right angles when they intersect? No. So it doesn't sound like that necessarily has to be the case. I don't know why this is so difficult. They just have to be different. If they're going to intersect, they have to have different slopes. And here's what should happen if you're going about solving them algebraically. So in other words, you either use the substitution method or you use the elimination method. If you solve it algebraically, you should get an ordered pair solution. You should get an x value, you should get a y value that you can write as an ordered pair. So if you're going to decide what type of system it is by its graph, all you're going to do is look for if they have different slopes or not. If you're going to decide whether it's what type of system it is by algebraically, now you're going to have to solve it and see what happens. You should get an ordered pair solution. That's one of the types of consistent. I want you to put a big fat or here in front of this too. Or it can't be consistent, independent, and this other one. It has to be consistent, independent, or it has to be consistent, dependent. When it is a dependent, a consistent dependent, that means it has infinitely many solutions. And that means when you graph them, you would have the same line. You would graph one of them, draw its line. You would graph the other one, it would be right on top of it. It would be the same line. Thus their slopes and y-intercepts are what? The same. They have to be the same. If they're on top of each other, they have to be the same. There's a name for those lines when you graph them, when you have two lines that have the same slope and y-intercept, or three lines, or however many. When you have a line, more than one line, when you have two lines or more that have the same slope and the same y-intercept, we call those coincident. You need to know this, especially for geometry next year. We call those coincident lines. So when we graph them, we end up with only one line on the graph because it's really one line on top of another. But when we solve it algebraically, here's what should happen. Both variables will eliminate. Not just one of them is eliminating. So you go about solving it algebraically, whether you're using the substitution method or you're using the elimination method. Instead of just the x's disappearing and there's y's left to solve for, or vice versa, the y's disappear and you have x's left to solve for, both of them are going to disappear. They both will eliminate. And you're going to end up with an equality. You're going to have a statement that doesn't have any x's or any y's in it, but whatever is left is true. It's an equality. You can say this is true. So far we have two types of systems. If we have a system that has at least one solution, it can either be consistent, independent, that's one name, that's one system, consistent, independent. How many solutions does it have then? If it's a consistent, independent system, how many solutions does it have? One, exactly one. Look, it's right here. Right here. Consistent, independent, exactly one solution. If it's consistent, dependent, the second type of system, if it's consistent, dependent, how many solutions does it have? An infinite number of solutions. All the points on that same line, every point, they're one's lying on top of each other, they have all those points are intersecting. They're on top of each other. So we have those two types of systems, and then we have our third type of system, and that is a system with no solution. And we call that an inconsistent system. No matter what you do, you cannot find a solution for it. It is an inconsistent system. There's only one type of inconsistent system, and it's the no solution one. So if that's the case, if there's no solution, that means the graph has parallel lines. If they're not intersecting, if they don't have any points in common, they have to be parallel. Well, if the lines are parallel, what can we say about their slope then? It's the same. What can we say about their y-intercepts? They have to be different. They have to be crossing the y-axis, though, at different places, or they would be coincident lines. They'd be on top of each other. So when we try to determine it by the graph, we have to see, do we have parallel lines or not? Then we know that we would have an inconsistent system with no solution. If you solve it algebraically, so you use the substitution method or you use the elimination method, same thing is going to happen as in that consistent dependent system. The variables will both eliminate. Both of them are going to disappear again. But this time, you're going to end up with an inequality. In other words, what is left has no x's in it, has no y's in it, and what it says is not true. One is not equal to the other. It's an inequality. Either it's less than or it's greater than the other. Okay, so in summary, here's what we should have, what we have to take from today. We have three types of systems. The first one being a consistent. So when you're naming them, this would be one of them. Consistent, independent. It has both names. That's one type of system. Consistent, independent. Consistent tells you there's at least one solution. Independent tells you there's only one solution. The second type of system is our consistent dependent. Consistent dependent, both names are needed. Consistent tells us it has at least one solution. Dependent tells it it has infinitely many solutions. And our last type of system only has a one name. It is called inconsistent. We don't have to give it a second part to its name. We just say this is an inconsistent system. So today you have to identify those. You have to decide, is it consistent independent, consistent dependent, or is it an inconsistent system? Okay, so here's kind of like what they're going to have you doing in your homework. Show that we have this system y equals negative 2x plus 2 and y equals negative x plus 3. You're supposed to show that has one solution. You get to pick the method you're going to use. Method 1 compares what would happen on the graph. Method 1 is what would happen on the graph. So let's just, put over here. You don't have to graph it, but this is telling you on the graph, this is what I could expect to happen. So we have y equals negative 2x plus 2, y equals negative x plus 3. Good news, they're both in graphing-friendly form. What's that form called? Slope-intercept form. So we can just go right to identifying the slope and y-intercept. So our first equation, what's its slope? Negative 2, and its y-intercept is 2. Other one? Negative 1 and 3. So when we're using method 1, we have to do this. We have to compare their slopes and their y-intercepts. If you're going to use method 1, this is what the requirement is. And then you're going to say, oh, okay, well now, what can I say about their slopes? Same, different? They're different. Is that a hard word to say or what? Negative 2, negative 1, they have different slopes. Well, if they have different slopes, we can just not even care about their y-intercepts right now. If they have different slopes, what do we have? What kind of lines? I just want to know what kind of lines we have on the graph. Intersecting. So at this point, once we decide they have different slopes, we don't even care about their y-intercepts anymore. We just say, oh, wait a minute, they have different slopes. These two have to intersect. That's what kind of lines I have. If they have different slopes that are that makes them intersecting lines, then yes, Macy, we're going to say this is a consistent, meaning there's at least one solution. And is it independent or dependent? When there's exactly one solution, they're going to intersect at one point. Independent. Okay? That's using method 1. Method 1 says you're going to talk about their graph. You're going to figure out what kind of lines would you have on the graph. Once you determine what kind of lines you have, that should help you be able to name the type of system. Or, let's put a big fat or over here again, you can choose to use method 2. Method 2 says solve it. Do the algebraic solving. So you can either use substitution or elimination. Which one does this kind of lend itself to being the better system, better method to use? Substitution or elimination? Are they in standard form? You could use elimination, but it's kind of better set up for substitution, isn't it? In other words, the first equation is the y's alone, so we could circle that expression. We could substitute that into the other equation for its y. So we're going to have 2x, negative 2x, excuse me, plus 2 equal to the negative x plus 3. Okay, go ahead and get that solved for x, because you already know how to do this, of course. You get negative 1 for x like I did? Okay, well, since we're actually using method 2, now we have to finish it. You're going to actually show what the solution is going to be. So we have to get the y value yet, right? So we could use either equation now to get our y. So I'm going to use the second one. And it appears our y value is positive 4. So we would say this is ordered pair negative 1, 4. So those lines, those intersecting lines, would intersect at ordered pair negative 1, 4. So this is one solution. And again, when there's only one solution, at least one says it's what type of system? At least one solution says it's what type of system? Consistent. Exactly one solution means it's independent. So this is typically what's been happening. We just haven't been giving it this name. We have been solving systems of equations, getting an ordered pair solution, and all along we were working with this type of system, a consistent, independent system. Now we have to be able to name them. We have to be able to identify that. So anybody have any questions about this one? In your homework, you have to show both methods. No. You get to choose. If you're going to choose method 1, though, what do you have to do? You have to compare their slopes and y-intercepts. And then after you're done doing that, you have to identify, okay, well that means, without actually graphing it, you would have to say, oh, this means what? They have, like this one had different slopes. Notice we wrote different slopes means intersecting lines. You have to write that. Different slopes means intersecting lines. That tells me there's going to be exactly one solution. Now I'm ready to give its name, consistent, independent. If I'm going to use the algebraic method, now I just go about solving it either by substitution or elimination. I see what happens, and then I can say, oh, I got exactly one solution for this one. I can now name it as a consistent, independent system. Okay, let's go to the next one, the next type. Show that y equals x minus 3 and x minus y equals 3 has infinitely many solutions. So I'm kind of giving it away. Show it saying, this should have infinitely many solutions. How are we going to prove that it does? So if we use method 1, we have to compare slopes and y-intercepts. Is the first one in slope-intercept form? Yeah, it's ready. What's the slope? What's this one's slope? 1, and its y-intercept? Negative 3. Is there other one in slope-intercept form? No. So what should we do to get it there? Add x to both sides. Why would we add x to both sides? Can we read subtraction backwards and say x is being subtracted? No. So we need to subtract x from both sides. Now what do we have? Negative y x equals 3 subtract x. And now what do we do? Divide every piece by negative 1. So negative y will get divided by negative 1. 3 will get divided by negative 1. I'm going to change this to plus a negative x. It's going to get divided by negative 1. So now I end up with y equals negative 3 plus x. Okay, what's the slope of this one? 1. What's its y-intercept? Negative 3. Okay? Remember, we're comparing their slopes and y-intercepts. What's true about their slopes? Same slope. So we would write same slope. What's true about their y-intercept? Same y-intercept. If they have the same slope and they have the same y-intercept, what's true? They're the same line. If they're the same line, that means what? How many solutions does it have? An infinite number of solutions, because every point it touches, there's several points that they share in common. So if there's at least one solution, it's what kind? Consistent. And if there's an infinite number of solutions, because it's the same line, it's what kind? Dependent. So this is a consistent dependent system. Do you have to write this part in your homework? Yeah. Same slope, same y-intercept, means same line. If you're using this method, that's what you do. That's how you justify that this has an infinite number of solutions, making it a consistent dependent system. Okay, now let's practice though, because, or, I want you to see what happens if you choose method 2 solving algebraically. Which method lends itself to this one? Substitution or elimination? Substitution, because the first equation is already solved for y. So we could sub it into the other equation for y. Or if you would choose to, you could get that set into standard form, that first one, and then you could use elimination if you want. Okay, so let's go, and so we're going to substitute into this equation. So we have x subtract x minus 3. So we're subbing into that second equation. Oh goodness, we have parentheses and all kinds of subtraction going on. This gets a whole lot of us in trouble. So maybe the best thing to do is to rename this as plus, and there's really a 1 in here. So we can make that plus a negative 1. This can be renamed as x plus a negative 3. Okay, go ahead and finish that up. x you should eliminate. You have a positive x at the beginning. After you do a distributive property taking negative 1 times x, you get negative 1x. We have a positive 1x. Added to it is its opposite, negative 1x. They cancel each other out. They eliminate. We end up with 3 equals 3. So we're going to write here that the variable eliminated and left with an equality. We can say it's an equality because 3 does equal 3. So the variable is eliminated and left with an equality. We solve it algebraically, and that happens. What kind of a system, how many solutions does that mean there are then? If the variables eliminate and you're left with an equality, what does that tell you about the solution? Go look at the front. If the variable is eliminated and you're left with an equality, what does that tell us about the solution?
Dependent.
Not type of system. Tell me about the solution. Is there one solution? Infinitely many solutions or no solution? There are infinitely many solutions. There are infinitely many solutions. That means there's at least one, so that makes it consistent. And when there are an infinite number of solutions, it's not independent. It's not one solution. It's dependent. So we have, again, 2 choices. Do we want to talk about what would happen on the graph? Do we want to talk about actually what would happen if we show what would happen if we solved it algebraically? Questions on any part of that one? 1 to go, and then we're done here. Okay, let's go to our last one then. Show that y equals negative 2x plus 5 and 2x plus y equals 1 has no solution. So if we're going to use method 1, the graphing method, in other words, we're going to talk about what would happen on the graph. Our first equation is ready to identify slope and y-intercept because we have to compare our slopes and y-intercepts. What's the slope? Negative 2. Y-intercept? 5. Our other one's not quite ready to identify slope and y-intercept yet, is it? What do we have to do first? Subtract 2x. After we subtract 2x, the y is now by itself, and it is a positive y. That's good news. We have 1 minus 2x. So Hayden, what's the slope of this one?
Negative 2.
Okay, Tate, what's the y-intercept?
1.
Okay. If we're using this method, we don't stop there. Now we write down what? That we're comparing their slopes and y-intercepts. So, Cameron, what's we going to say about their slope? Negative 2, negative 2. Same. What are we going to say about their y-intercepts? 5, 1. Different. If we have same slope, different y-intercepts, what does that tell us about the graph? We have what? Parallel lines. Parallel lines. If we have parallel lines, will they ever intersect? No. So that means there's what? That means no solution. There is no solution to this one. If you got parallel lines, there's no solution. So what kind of a system do we have? Inconsistent. When it's inconsistent, does it have another name? No. So method 1, comparing their slopes and y-intercepts, what does that mean after you say what is true about their slopes and y-intercepts, that means, oh, well, this is what kind of lines we would have on the graph. That kind of lines tells me that we have no solution. That tells me what kind of a system I have. Okay, method 2, solve algebraically. Go, do it. Every one of these seems to just want to be, shout out that they're going to be, but you know what, I think I'm going to be different this time. I think I will take this one and I will get it in standard form. So I can use elimination because it's my favorite way. Well, I gotta rename it, don't I? Okay, so now I'm gonna rename it by multiplying by -1 so I can get opposites. Too much going on here. Crazy mistakes here. Oh, So I use the elimination method because I was kind of tired of using the substitution method. I got the first equation put into standard form. Then I renamed it by multiplying by -1. Here's its new name. And then I added it to the other equation. And I ended up with the x's cancel away, the y's cancel away. That means there's got to be something left on that side. Well, it's 0. When there's nothing, it's 0. So I have 0 equal to -4. What happened when you did it by substitution? 5 equals 1. Anybody get something else? 5 equals 1 is what you got? Okay. So basically what happened? The variable is what? In both cases, the variable is what? Eliminated. So write this down. The variable is eliminated. And left with what? Did you get an equality or an inequality? An inequality. 1 does not equal 5 any more than 0 equals -4 in my case. So left with an inequality. Well, if that's the case, then that means there's no solution, right? If the variables eliminate and you end up with an inequality, that means you have a no solution and we have an inconsistent system. So you have to do either method 1 or method 2. Don't do them both. You don't need to do them both. But whichever one you do pick to do, you need to refer to your notes to help you see what kind of support you have to have for your answers. And then when they say classify a system, that's what we're doing right here. We call it an inconsistent system, or we call it a consistent dependent system, or we call it a consistent independent system. We are classifying it. We are giving it its classification. So anybody think they're unclear what the expectations would be for how to show work for this stuff? Which method do you think is probably going to be the shortest? 1. Probably, yeah. That means you get to pick.